Welcome to, sadly, our final section that you will get from me for the spring semester of 2020. What we're finishing off with here in Chapter 4 to build off of what we did in the last two sections is logarithmic functions. And as I mentioned in the last section of notes, exponentials and logarithmic functions are inverse functions of one another. So what I like to stress, and I know I've said it with a couple of different things this year, everything that we learn how to do in math, we learn the opposite process for, right? Factoring is the opposite of the FOIL process. Squaring is the opposite of square root, something that's very basic. Likewise, these logarithms, these functions, are the opposite or the inverse functions of the exponentials that we saw in the last section. Okay. So this is what logarithms allow us to do. So let's look at these two quick questions that I have on this board right now. It says, for which value of x will 8 equal 2 to the x power? So you can see we kind of know our final answer. So think flipping input and output. What I don't know is what exponent gave me 2 raised to that power to equal 8. And that's a pretty easy one to answer. It's 2 to the third power. 2 times 2 times 2, that gives us 8. All right, so the answer to that question is 3. However, what if I go to something like this? 17 is equal to 3 to the x, and I try to answer that same question. The answer is, this is not so easy. Right? 3 to a power, all right, well, 3 to the third, 3 squared is 9, 3 to the third is 27. So I know that I'm somewhere between 2 and 3, but I don't know an exact value for that. That is what logarithms allow us to do, and unfortunately we're not going to get too in depth with them, but that is the whole basis for it, is how can I solve for any exponent that I need to find in a given function. So next we have the general form of what a logarithmic function looks like here. So the first thing we start off with in the labels, y is equal to log base a of x. That's how it's read, log base a of x. So there will be values here, of course, when we're actually finding specific exponents. But so this base here, that's where it always is. So in this case, if I compare it to one on the board, that base was 2, right? The part being raised to the power. The argument is what I like to think of as the original output. So in that case, it would have been 8 in this first example that we did. Just a couple of other parameters. The base that we're talking about will be greater than 0. Doesn't really make sense to talk about 0 to any power because it's still always going to be 0. With x not equal to 1. Okay. Now this is going to be very important. This, where I have this or, these two are equivalent. These two forms here. This is going to be the more convenient form, I guess, to be able to work with. It allows us to see it a lot more clearly. And I think a lot of times, if you've seen these in the past, logarithms, I think people lose sight of what they mean. And so what I want to stress here, this is very important. The output, or you can think the final answer, of a logarithm is an exponent. Keep that in mind as we go throughout these questions here today. So the output of a logarithm is an exponent. Okay, so again, the rewrite step that's going to be important, and these problems are very quick that we're going to see today. Okay, so if I have something in the form of this, a is my base, x is, like I said, kind of my original output, and y, the answer, again, is the exponent that base is raised to give us what that argument was. So again, when we see some specifics here, I think it'll be a lot more clear. But those are the two forms that you do need to make sure you're comfortable switching between anyway. So these examples that we'll see, again, they move very, very quickly. We'll say solve for y. Number 1, y is equal to log base 3 of 9. Okay, so again, keep in mind, the output that we are looking for is a power. Here's how we do this rewrite, and that's why I stress this is the more convenient way to think through these. All right, so here's where I start. This is my base. This, my output, is the exponent. So the question is 3 raised to what power is equal to the argument of 9? and now hopefully that we see this is a pretty quick question to answer. 3 to the second power is equal to 9. So y is equal to 2. It is that simple, at least these basic ones, as we do the rewrite step. Number 2, log base 3, y is equal to log base 3 of 3. Once again, the rewrite step, my base is 3, raised to what power equals 3. Well, if the base and the output are the same, it means that exponent just has to be 1. So 3 to the first power keeps it the same. Number 3, y is equal to log base 4 of 2. All right, so we're going to see some exponent properties that we'll have to refresh on possibly in this question. Once again, the rewrite, 4 to the power of y is equal to 2. All right, well, how do I take a base and get an output that is smaller when raised to an exponent? The answer to that question is that it is a rational exponent. Think of it this way. Rational exponent and square roots many times pair together. So here's how I get here. We know that the square root of 4 is equal to 2. The answer then to the question is, what is the same thing as saying the square root of by using a power? And the answer to that is, it's a fractional power. 4 to the 1/2 is equal to 2. So that means my exponent is that. It's 1/2. Okay. Number 4, y is equal to log base 5 of 1. All right, so again, do the rewrite, and then let's think through what exponent property is going to be used here. 5 to the power of y is equal to 1. So the answer to this question is any term raised to a power of 0 gives us an output of 1. So our exponent here is 0. And that's it. All right. Last one of this section. And number 5, y is equal to log base 2 of 1/8. Now we saw things with fractions in the exponential function section. Once again, do the rewrite. 2 to the y is equal to 1/8. The way that we get fractions, remember, is with negative exponents. So think of it this way. If 2 to the third is 8, 2 to the negative third gives us 1/8. So the reciprocal, right? So this is negative exponents. Again, something that we reviewed a couple sections ago. But again, that is how we find the values of basic logarithms. The last thing that we'll finish up with here in this section is, again, with exponentials, we did a little bit with input and output, but we also saw what did their graphs look like, and that's what we're going to also see with logarithmic functions. So we have a new parent graph with logarithmic functions. Okay, and I'll just do a quick sketch here, and then I'll list the characteristics off to the side as I do it here. So this is the parent graph of y is equal to log base a of x. The characteristics. First, now what I want to stress, maybe you can come up with this list on your own just by me saying this. Every characteristic that was true about exponential function parent graphs, it is going to be the opposite, or the inverse for logarithms, because they are inverses of one another. So, first of all, let's build the graph a little bit. So with exponentials, I think the first thing I wrote was that there's a horizontal asymptote at x equals 0, or y equals 0, the x-axis. Therefore, there is going to be a vertical asymptote at x equals 0. All right, so remember, back to last section, an asymptote, kind of that, not really a part of the graph, but it's a guideline that our graph will approach, but it will never cross. So it can never cross a vertical asymptote. Okay, but again, we're going to get closer and closer to it when I actually sketch the figure that the parent graph makes. Secondly, exponentials had a y-intercept of 1. Therefore, logarithms have an x-intercept at 1, 0. So remember, the whole idea with inverse functions is the inputs and outputs reverse. So that point is always there on the parent graph. Again, think anchor point. This is the one that we're going to shift around anytime there are translations. Number 3, there is no y-intercept on a logarithmic function graph. And the reason for that, that's where the vertical asymptote is. Remember, a graph cannot cross a vertical asymptote. Number 4, the domain are all numbers greater than 0. Our range, all real numbers, or negative infinity to positive infinity. And again, if you check your notes from the last section, those two are exchanged. And finally, just like exponentials, they are continuous. All right, and now last thing to add to the graph, here's what the general shape of a logarithmic function takes. Okay, and once again, the graph itself gets closer and closer to that vertical asymptote as it goes down towards negative infinity, but it can never cross it because we have no y-intercept. So there's the parent graph, and now what we're going to finish off with is just a couple of examples of graphing them. Number 1, y is equal to log base 10 of x. So remember, with these, I'm not asking you to be very specific other than with where your anchor point would be. So for this one, if you look, there are no translations. There's not a negative anywhere making it reflect. There is not a number added or subtracted at the end of the function or next to x that would cause it to shift in any way or another. So again, the two things that I'm going to require for all of the graphs is, first of all, where is the vertical asymptote? If there was no shift, it means it is going to be on the y-axis, just like the parent function. Okay, so again, there's your vertical asymptote at x equals 0. As before, again, this one involved no shifts, which means that the parent graph's x-intercept is not going to change. It's still going to be at 1, 0. All right, and again, once you have labeled those two things, that is as specific as I need you to go. So we can now do our general shape of the graph. And again, I know it's not a perfect sketch by any means, but once again, the graph gets closer and closer to that asymptote, but we'll never touch it as you go farther towards negative infinity. Okay, number 2. Number 2, y is equal to log base 10 of x plus 2. All right, now, parentheses in this case are very important. Because there are parentheses there, that means that plus 2, that's going to cause a shift horizontally, not vertically. If there were no parentheses and the number would therefore be added at the end, that would shift it up and down. So our shift in this case, hopefully you remember this from last section, this is going to shift left 2 units. So remember, the opposite sign of the one grouped with x, that tells you the direction of the horizontal shift there. Now, what I always want to stress, with exponential functions, the horizontal asymptote shifted with the vertical shift. Therefore, we're going to exchange that. The vertical asymptote will shift in correspondence correspondence with a horizontal shift, okay, along with our anchor point. So what I'm going to label here, and then I'm going to translate it to the graph. Okay. Now, I am shifting left 2 units, which means that this point is going to also have to shift 2 units to the left. So instead of 1, 0, let's count 2 away from that. 1, 2 lands us at the point -1, 0. Okay, so again, that will also directly correspond with any horizontal shift. Last, that vertical asymptote, once again, that's always going to be 1 away from that anchor point. So if this is our new anchor point, it means that if our vertical is normally at x equals 0, vertical asymptote is now going to be at x equals -2. All right, so once again, now we can graph it using those 2 pieces of information. And if you have these 2 graphs side by side in your notes, you'll notice you'll notice it really is the exact same picture with everything shifted 2 to the left. So my new anchor point, as we said, is at -1, 0. Our vertical asymptote is now at this line, x equals -2. Okay, so once again, those are the 2 things I'll want you to label, and it will have the same general picture as our last one did there. And so again, anchor point and vertical asymptote are all that I want you to label for these. Last one here, maybe try this one on your own, will involve a couple of shifts. Number 3, y is equal to log base 10 of x minus 1 plus 3. So once again, let's describe the shifts, translations that happens here. First of all, the number grouped with x, we can start there. Since it's a -1, that means we shift right 1 unit. So think that is the measurement that we will base our vertical asymptote and anchor point on now. And also with a +3 at the end, that shifts our graph up 3 units. Okay? And once again, to come up with our graphing information, our anchor and our vertical asymptote. So once again, we're going right to the horizontal shift to make sure we pair this information with it. So once again, let's kind of think through this one, instead of me going to the graph. Again, if the anchor point is normally at 1, 0, 1 unit to the right of that would be 2, 0. However, actually, hopefully, well, you can erase it or cross it out. The 2 is correct. So I had to shift 1 unit horizontally. Hopefully you can catch the mistake I just made though. Because I'm also involving a vertical shift, that is going to change my y value. So instead of 2, 0, it's actually going to shift to 2, 3. Because I have to also take into account the vertical shift that we made. Vertical asymptote, once again, is always going to directly correspond to the shift that we made in the horizontal direction. If the vertical asymptote is at x equals 0 with the parent, it means this one will now be at x equals 1 with a horizontal shift to the right 1 unit. So now that we have that information, once again, we have enough to graph. So 2, 3 is our initial point, with the vertical asymptote always being 1 unit left of that. Okay, so in that case, there we go. There's vertical asymptote at x equals 1. Our anchor at 2, 3. And once again, keeping with the general shape of our parent function. All right, so there we go. There is, again, kind of an introduction to logarithmic functions. Would love to go more in depth with it. Unfortunately, for the sake of time, that'll be all we get to with the basics. So again, most important things, how do we find the values of basic ones, and the new parent graphs that correspond in an inverse relationship with exponentials. So as usual, I'll put up the suggested homework, and hopefully you had a great semester. I know I did, and have a great summer, and I'll be in touch soon.